Hi guys, this is Smartphysics tutorial for right triangle or right triangle. Wow. Hi guys, this is Smartphysics tutorial for the right triangle current loop. Okay. Here we have a triangle, loop triangle, and the current is going this way, and we have a magnetic field that's pointing out of the screen. So we have these known, which is AB. We have BC. We have the current that's going through this loop, and we have the magnetic field known. Okay, so the first question is asking, what is the force on AC? They want the x component of that. By the way, you can see the question description below. Alright, so they want FAC x. Okay. So the force here is equal IL cross B, and the cross product here can be we can ignore it because the B is always perpendicular to the AC here, to this length. Okay, because this is the length, the AC, and the magnetic field is always perpendicular to it. Cool. Okay. But they want the x component of it. But let's see what is the direction of the force here. So it's IL cross B. So IL cross B. Here's the AC, and here's the current going this way. So if we put our fingers with the L and the I, and cross it with the magnetic field, then it's going to be pointing this way. So this is the force, it's pointing this way. Okay. So they want the x component of it. So if this is theta, this is 90 minus theta. Okay. And the L here, we can find it from Pythagoras, because we have this length and we have that length, which is so L here will be equal to square root of AB squared plus BC squared. Okay, you can find the L this way, and the B is known, so it's FACX is equal to I is known, L you find it this way, and then B, and then we do the cosine of 90 minus theta. Alright, let's get the theta now. So the theta, you can find it by, since this is the theta, you can do the tangent, because you know this and you know this. So it's tan inverse of the BC over AB. This is how you find the theta. Make sure it's in degrees though. Okay, then you plug it back in here and you solve for this equation. Alright, so number 2 is asking what is FACY? So FACY, they want the y component of this force. So it's the same thing, we just change this to sine. So it's ILB sine of 90 minus theta. Cool. Let's watch for the directions here. So the y will be in the positive, and the x will be in the negative, x minus. Okay, make sure you do that, because look here, the y is going up. If we say that the positive y is going up, and the x positive is to the right. Okay, so the y is going up, the x is going to the left, which is negative here. Cool. Alright, so number 3 is asking, the wire now is rotated 180 degrees above the y-axis position 2 as shown. Anyway, read the question by yourself, it's down. Alright, so number 3 is asking, they want the delta U, y2. Okay. So let's find y initial. So the potential initial is equal to minus U dotted with B. Okay, u dot b. So the u here, if you look at it here, if you want to find the direction of u, it's if you curl your fingers with the current, so if it's going this way, so curl your finger this way with the current, and then your thumb will be pointing with the dipole moment, yeah, magnetic moment. Okay, so it's going up, and the magnetic field is pointing up to. So to change this, so this is, we can write the same as u times b times the cosine of the theta, the angle between the b and u. Okay, and the theta here, because both of them are in the same direction, then the theta will be equal to 0. Okay, the theta will be equal to 0, and cosine of 0 will be 1. Okay, cool. So the u final now will be equal to look at the u final now here. The magnetic moment is pointing into the screen, okay, and the magnetic field is pointing out of the screen. Cool. So the angle between them is cosine of 180 degrees, and this will change it to minus 1. So the u final will be equal to ub. Okay, very cool. So the delta u is equal to u final minus u initial, which in this case will be u final, which is ub, and then minus, which is positive, ub. So it's equal to 2ub. Cool. Cool. Alright, so number 4 is asking, let's fix this. There's enough room. It's asking, the wire now is rotated back 90 degrees toward position 1. Okay. If the wire is released from this position, how would it move? Okay, so we took like here it's like, let's talk in potential energy, like something we know. So here's the potential is 0 here, and we took a ball and left it to like height h. So here's the ball here. Okay, so it gained potential energy here, right? And if you release it, it will go down. It will go back to the position it was in, right? So if you take it like half the distance, like it's the same here because they rotated 90 degrees, and so if we took it to this point, it's still going to go back to the position it started, right? So it, in this question, it's going to go to position 2. Position 2. Cool. Alright, so number 5 is saying if they rotate this loop, they rotate it like here we rotated this, and in the 5th question they asking if they rotated from this side to here. Okay, see the difference? So it's gonna look like this. C is here, B is here, and the A is here. Okay, and they're asking about the potential energy, the same thing. Well, if you look at the equation, it's u dot b, right? It's minus u dot b. Well, none of them like depend on the way it's gonna turn. It just depends on the dipole moment, the area, which is IA times b, right? So it doesn't depend on anything. So the answer you're gonna get here is the same. Okay. And by the way, this is like 2, and the dipole moment is IA, B, and the A here is the area of the triangle, which is half BA BC. Okay. Right, so to change it from this position to this position, it's the same as changing it from this position to that position. So the answer for 3 is the same as the answer for 5. Same as 3. Alright, cool. Well, I hope this helped you, and good luck.